Now we have seen the possible pairs for the octahedral complexes of the type Ma2B2CD. Now let's come to the calculations, that is the calculation of the geometrical isomers, optical isomers, enantiomeric pairs and stereoisomers. So we know that the number of geometrical isomers is equal to the number of the possible pairs and the number of the possible pairs for your octahedral complex of Ma2, B2, CD was 6. So the number of geometrical isomers is also 6. Next we come to the number of optical isomers. So now first of all let's just write whatever we know that number of geometrical isomers is 6. And I had already told you that the number of optical isomers, in the calculation of the number of optical isomers, you will have to see only those which are optically active. The optically inactive pairs you have to forget about. So the number of optically active pairs were 2. There were 2 optically active pairs and 4 optically inactive pairs. So 2 optically active pairs are going to give you 4 isomers, because 1 optically active pair gives you 2 isomers, that is dextrorotatory and levorotatory. So 2 optically active pair will give you 4 isomers. So the number of optical isomers is 4. Now next is the number of enantiomeric pairs. Now let's just fill in the details you already know. So number of geometrical isomers is 6, number of optical isomers is 4, number of enantiomeric pairs. And I had told you that the number of enantiomeric pairs was the number of optical isomers divided by 2. So the number of enantiomeric pairs is 2. Next, now we come to the number of stereoisomers. Again, fill in the details you already know. So this is 6, this is 4, this is 2. The total number of stereoisomers were equal to the number of optical isomers plus the optically inactive pairs. So that's 4, and the optically inactive pairs were also 4. So 4 plus 4, which is equal to 8. So these are all the total possible geometrical isomers, optical isomers, enantiomeric pairs and stereoisomers possible for the complex Ma2, B2, CD. Now we have the complex, octahedral complex of the type Ma2, B2, C2. So in Ma2, B2, C2 there are 3 different type of ligands, A, B, C, and all of them are present twice. So that still gives you an overall coordination number of 6. So now let's see the possible pairs for this octahedral complex. So first is AB, AC and BC. That means A is trans to B, A is trans to C and B is trans to C. So in this, none of the same ligands are trans to each other and a trans pair is also not getting repeated. So this means this is an optically active pair. Now let's go to the next one. This is the next possible pair. In this, A is trans to A, B is trans to C, B is trans to C. In this, what is happening? The same ligand is trans to each other. A is trans to A. Moreover, 2 trans pairs are getting repeated. There is BC and then there is again BC. So this is optically inactive. So till now we have seen 2 geometrical isomers, one of them optically active, the other optically inactive. Now let's see if there are more possible pairs. Yes, there are more possible pairs. In this, A is trans to A, B is trans to B and C is trans to C. So this is obviously optically inactive because all of the ligands, same ligands are trans to each other. A is trans to A, B is trans to B and C is trans to C. So this is also optically inactive. So 3 possible pairs, 2 optically inactive and 1 is optically active. Now let's go to the next possible pair. Now this is the next possible pair. In this case, B is trans to B, A is trans to C, A is trans to C. Again, B and B are trans to each other, that means it is optically inactive. AC, trans pair is getting repeated. So both of the conditions are there, that is the same ligands cannot be trans to each other and trans pairs cannot be repeated. So both of these conditions are there, so this is also optically inactive. Now this is the next pair. In this, C is trans to C, A is trans to B, A is trans to B. Again C is trans to C, so this is optically inactive and trans pairs are getting repeated. AB, AB trans pairs are getting repeated, so this is also optically inactive. So these were all the possible pairs for the octahedral complex of the type Ma2, B2, C2. So now we'll have to see what will be the calculations, what will be the geometrical isomers, what will be the optical isomers, what will be the number of enantiomeric pairs, and what will be the number of stereoisomers. Okay, first of all, number of geometrical isomers. Again, number of geometrical isomers is equal to the number of possible pairs, and the number of possible pairs were 5. So the number of geometrical isomers is also going to be 5. So let's just write 5 here. Next we come to the number of optical isomers. So fill in the details, you already know, this is 5. Now the number of optical isomers is dependent only on the number of optically active possible pair, and that was only 1. So one optically active pair is going to give you 2 isomers. So that is 2. Next is the number of enantiomeric pairs. So again, first of all, you fill in the details, you already know. And the number of enantiomeric pairs is equal to the number of optical isomers divided by 2. So that will be 1. Then the next is the number of stereoisomers. Fill in the details, you already know. So that's 5, that's 2, 1. Now the number of stereoisomers is equal to the number of optical isomers plus the number of optically inactive pairs. So the number of optical isomers is 2 and the number of optically inactive pairs is 4. So that's 2 plus 4, which is equal to 6. So the complex, octahedral complex of the type Ma2, B2, C2 has 5 geometrical isomers, 2 optical isomers, 1 enantiomeric pair and 6 stereoisomers in total. Now we have the next octahedral complex is of the type Ma4BC. Now there are 3 different types of ligands again, but one ligand is 4 times and the other 2 ligands are 1 time each, which still gives it an overall coordination number of 6. Now possible pairs. This is the first possible pair. In this, A is trans to A is trans to B, A is trans to C. So in this, it's optically inactive because the same ligand is trans to each other. So it's optically inactive. So this is an optically inactive pair. Next we come to the next possible pair. In this, A is trans to A, B is trans to C, A is again trans to A. So in this, first of all, you can see the trans pair is getting repeated. 2 pairs are same, AA and AA. Moreover, the same ligand is trans to each other. A is trans to A is trans to A. So this is also optically inactive. So these 2 are the only possible pairs for the complex of the type Ma4BC. And both of these are optically inactive. So we have no optically active pairs for this type of octahedral complex. So in the next slides, we are going to see the calculations related to the number of geometrical isomers, optical isomers, enantiomeric pairs and stereoisomers.